6, 5. Welcome to the Space Telescope Public Lecture Series. Tonight's talk, A Tapestry of Gravity, LISA and the Future of Gravitational Wave Astronomy by Dr. Shane L. Larson from Northwestern University. I'm Dr. Frank Summers as your host, and it is my pleasure to be with you each and every month. I want to thank our tech team. Grant Justice is with us tonight, but Thomas Marufu had an emergency, so the part of Thomas Marufu tonight is being played by the inimitable Kevin Flynn. Thank you, Kevin, for the last-minute fill-in. And I want to remind you that the Space Telescope Public Lecture Series is now permanently online only. I know there are a lot of people here in Baltimore who love to come in and see the lectures being given live, but I'm sorry, we're going to continue in an online only format. Our upcoming talks next month, very exciting one. We're talking about the total solar eclipse of April 2024. All right, this is another total solar eclipse that's coming across the U.S. All right, and you got to prep for it. Michael Kirk from NASA Goddard Space Flight Center and John Maple from the Space Telescope Science Institute will help you get ready for that eclipse. On April 2nd, I actually have a speaker, but I just haven't confirmed everything, so I didn't want to put it up here until it's fully confirmed. But April 2nd, we have a speaker, so that TBD is halfway been determined, but we'll get there real soon. I'll get that done next week. On May 7th, Stellar Astronomy in Search of Dark Matter, Eduardo Vitral of the Space Telescope Science Institute. And if you want to check on this and find out when I've got that April lecture scheduled, you can go to stsci.edu/public-lectures. And you can see in the lower left, you can watch all of our webcasts, both on the STSCI webcast archive and our playlist on YouTube. And in the lower right is the place where you can subscribe to get monthly reminders, basically 2-3 emails a month reminding you of the lectures and when they are posted, when the webcasts are posted for viewing. Also on the website, you'll find, of course, the list of the talks. And if you click that read more button about each talk, you'll find the details, including after it's been recorded, a link to the STSCR webcast and the playlist, the video on YouTube. Email, as I said, sign up at the website. But you can also subscribe to our YouTube channel, youtube.com Hubble Space Telescope. If you sign up there, you'll get new video notices and reminders of live events such as this. If you have comments or questions, you can send them to the email address publiclecture@stsci.edu. Our social media, we run for the Hubble Space Telescope, for the Webb Space Telescope, and for our Institute. On Facebook, on X, on YouTube, and Instagram. And now our news from the universe for February 2024. Our first story tonight, the search for water continues. Now, looking for water is very important because there are 3 requisites for life as we know it. The first requisite is an energy source, like a star. And there are plenty of stars out there in the universe. So lots and lots of energy sources out there. And then you need carbon chemistry. And, carbon's pretty common in the universe, so there's lots and lots of carbon out there. The third thing you need for life as we know it is water. Water as the mediating fluid for that carbon chemistry. All right? And so energy and carbon are abundant. So if we want to find a place where life can develop, we're really looking for places where there is water. Now, on our planet, you can see there's water because, we're up nearby it and we can look at it and see we're covered in 2/3 of the surface is water. But what about other planets, extrasolar planets or exoplanets as they're called? not so much. We don't have quite so good views. This image I'm showing you on the right, that X marks where the star would be, but its light had been blocked out and removed digitally. And you can see that there are 3 planets around it, and they're just fuzzy blobs, and we're barely able to see them on this. But we can actually tell if there's water on some exoplanets, because sometimes an exoplanet, as shown in this artist's illustration, will pass in front of its star from our point of view. In that case, the light from the star goes through a little bit of the atmosphere and imprints the characteristics of that atmosphere on the light. And what we can do is we can subtract off the light from the star, leaving behind just the light that has passed through the atmosphere. And we understand characteristics of that atmosphere. And in that, we can actually discover elements in the atmosphere like water. Water has been discovered in several planets out there, but most of them are Jupiter-sized planets, really, really big planets. And you know what we're really looking for? We're trying to see if there's another Earth out there, and if it's got water, and if it could have life, right? Well, we made a significant advancement with Hubble in the last month or so. On this planet, GJ 9827d. Okay, so in this artist's illustration, the star there is GJ 9827. All right, and then there are 3 planets in this illustration, B, C, and D. And the one that's really interesting is D. And planet D passes in front of the star from our point of view so that we can measure it and we can find the elements in the atmosphere. And we found water in it. What makes this more exciting than previous ones? Well, the size of planet GJ 9827d is what makes it exciting, because its radius is twice Earth, its mass is 3.5 times Earth, which actually, if you do the radius over the mass over the radius, you can see that its density is about half that of Earth. Okay, so we're getting down to an Earth-sized planet and finding water around it. But I got to tell you, you can't get too excited about this one, unfortunately, because we can't tell whether the water is just sort of in a hydrogen-rich atmosphere, and that this 3.5 Earth mass thing is actually a mini Neptune, right? Or it could actually have a rocky core with tons of water and tons of liquids on it to get down to that density, and that would be a water-rich super Earth. All right, we can't tell now. We might be able to tell with further study on it. But the other reason not to get too excited about it is that this planet orbits really close to its star, much closer than Mercury. All right, and so it orbits in 6 days. It has an orbit around the star only 6 days, which means it's really hot. It's actually as hot as Venus is at 800 degrees. So if it does have a lot of water, it's quite the steamy world. But the significance of all this is that we're now pushing down below the Jupiter-sized planets, below the Neptune-sized planets. We're starting to push toward the Earth-sized planets. And as one researcher described it, water on a planet this small is a landmark discovery, as it pushes closer than ever to characterizing truly Earth-like worlds. So we aren't there yet, but we're working on it. Our second story, detailed galactic structure with fangs. And those of you who are perennial watchers might recognize that I did this exact same story a year ago. But it's now new and improved, okay? So let me remind you of what I told you a year ago. Fangs is physics at high angular resolution in nearby galaxies. And you can see the incredible lengths astronomers go to come up with these acronyms that they can call their project. This one's really working hard because you got to do the first 2 letters in angular, and you got to use the S at the end of galaxies to get it together. Yeah, some astronomers just work way too hard at things like that. But anyways, the point is we're looking at the nearby galaxies, and we can see them with really great resolution, so we can actually study what's going on in their cores. All right, and so FANGS is actually a multi-telescope survey. It started with the ALMA, the Atacama Large Millimeter Array, and here is the molecular gas disks in some of these galaxies. They did 90 galaxies with Atacama. And then they moved on to using the MUSE, the multi-unit spectroscopic explorer on the Very Large Telescope. And based upon that, they were able to successfully apply for HST, the Hubble Space Telescope. And they observed 38 FANGS galaxies with Hubble. And then who are you going to call now? You're definitely going to try and get FANGS on JWST, the Webb Space Telescope. And so what I told you about a year ago, almost a year ago, was the first results from FANGS, in which I showed you these two images from Webb in the mid-infrared. Okay, the Webb Space Telescope has near-infrared and it has mid-infrared, and they see significantly different things. All right, especially if you want to see stars, you got to go to the near-infrared, and then the dust shows up much better in the mid-infrared. So these first two galaxies that I showed you were from the mid-infrared only. Well, it's new, it's improved. We now have the near-infrared, and the FANGS galaxies now look like that. Yeah, kind of cool, detailed, a lot more richer when you get both the near-infrared and the mid-infrared into it. And I should note that the galaxy on the right, 7496, it looks like it has this starburst in the center. That's actually an active galactic nucleus, okay? It's a supermassive black hole that's so bright in the mid-infrared, it actually produces the diffraction spikes that make it look like a star. That's how bright the supermassive black hole is in the infrared, mid-infrared. Okay, but we can also compare these against the Hubble images. Okay, so there we go. We've got the Webb and we've got Hubble. All right, you can see the crazy differences between them. All right, and then maybe we'll take some nice spiral galaxies. Look at these beautiful spiral patterns here in the center. This is what you see in Webb. With Hubble, and now here's what you see in Webb. Oh, this is just so cool because you're seeing all that dust structure that underlies, that's hidden. In visible light, it's all brown and it's all sort of hidden by the star emissions. But in infrared light, you see those stars disappear for the most part. You can see them there in the core, that blue core, but you also see that sort of cellular-like structure of the dust, okay? And this is the really cool physics that's going on that's creating all this structure in these galaxies. And then you could do a couple of galaxies that are barred spirals, and you say, I don't see the barred. Well, NGC 1300 is one of the most famous barred spiral, but you really only see the bar in Hubble. Okay, there's the bar, and Webb doesn't see it. 1566 has a bit of a bar there as well in the center. All right, and so you can see the structures, how they change as you go from visible to infrared. And really, you can play this game for quite a long time because we released 19 FANGS galaxies, okay? 19 images of galaxies in the infrared with detailed structure, and you can see all the stuff that's going on internally. So they is looking at the physics of that's happening in the within the galaxy, looking at high angular resolution because these are nearby galaxies, and really getting to sink our teeth into some really juicy images from FANGS. All right, our speaker tonight is Shane Larson, and he comes to us from Northwestern University, where he is a professor in the physics department there. He is also the associate director for Sierra, and I can't remember what that is, so I have to look it up, read my notes. Center for Interdisciplinary Exploration and Research in Astrophysics. One of these not quite so tortured acronyms because it actually makes sense. His specialty, as you might guess from the title of his talk, is gravitational wave astronomy. He has worked with the ground-based LIGO project, measuring gravitational waves from the ground, and he is also on the NASA study team for LISA, the space-based gravitational wave satellite that has been proposed. He formerly was a professor at Utah State and is a fellow of the American Physical Society. And as you can see on your screen now, he does a lot of outreach, he has a WordPress blog, and his Twitter handle, or I guess it's his X handle now, is Science Jedi. All right. So, ladies and gentlemen, Shane Larson.
Okay. Well, thank you, everyone. Certainly thank you, Frank, and the team at STSCI for the invitation. It's always a great pleasure to be able to come and talk to people about things that are very near and dear to my heart. I am at Sierra at Northwestern. We are a Center for Interdisciplinary Astrophysics. So we are a collection of many scientists at all stages of our careers, students, postdocs, faculty. We work on all different areas of astronomy. We overlap with exoplanets. We do high-performance computer simulations. We work on data science applied to new massive astronomical data sets. We have observers who study transient astronomy and do spectroscopy on the Webb Space Telescope. But we also have gravitational wave astronomers, and that is what I work on. I mostly work on LISA, which is what we're going to talk about tonight. LISA is the Laser Interferometer Space Antenna. And for those of you who've been paying attention to the news, this has been a big week for us. So LISA is a joint project being led by the European Space Agency and NASA as one of the junior partners on that experiment. It has an idea that has been around for 40, 50 years at this point. But just in the past week, it was formally adopted, as we say in the space biz, by the European Space Agency and the member states. And so what that means is we are actually moving forward. We've done all our design studies. We've talked about our science. We've demonstrated that our technology is doable. And so the European Space Agency has formally voted that it's time to start moving forward. So within a year or so, the formal aerospace contractors will be selected. They'll go off and figure out how much titanium and duct tape costs, and we will build this space mission to be launched in the next 10 years. So what I want to do tonight is I'm going to tell you, I'll kind of put this all in the context of astronomy that you may be familiar with. I'll introduce you to gravitational wave astronomy for those of you who haven't been exposed to it before, and then we'll talk about what LISA is, how it's going to work, and some of the science that we hope to do with it. As Frank said there, my blog is there, that is public facing. As I tell people, it's so my mom knows what I do. So there's a lot of stuff about LISA and gravitational wave astronomy there. There's other stuff about black holes and the lives of stars and various things. There will be a new post about LISA in the next couple of days about the adoption that I just told you about. So if you're interested, you can certainly go follow it there. Okay? So for those of us who are astronomy enthusiasts, pictures like these right here are not unfamiliar. They are very indicative and representative of a whole generation of us who really grew up in an age where astronomy was a golden science. It's easily accessible. There are really remarkable discoveries being made all the time, and that information has been readily transmitted across the country and the world through initially all kinds of media, television, magazines, newspapers, but today almost instantaneously through the internet. And so we've kind of arrived at that time in our civilization where you can show pictures like this and they are not necessarily unfamiliar to people, even if they themselves have never looked through a telescope. These are the capturing of the kind of collective knowledge of our civilization that has been gathered by astronomers using remarkable technologies. And so that's really part of the theme tonight, is that these views, this understanding that we have of the universe and our place in it and what it means about where we're going, where we've been, and what the ultimate fate for all of us is really enabled by our ingenuity and our ability to harness technology to give us these remarkable views. That technology, of course, began with telescopes, and telescopes are something that those of us who are amateurs can certainly use in our backyard. We often get, the same disease that professional astronomers have, and we want bigger telescopes. So you can see that's my current telescope, which is much larger than the original telescope I had. But lots of the understanding that those of you who aren't professional astronomers have about the universe has been learned through these remarkable machines that Frank was talking about before the talk began, namely the Hubble Space Telescope there on top and the Webb Space Telescope there on the bottom. These instruments, and Hubble for 30 years now, and James Webb is just at the beginning of its journey, have literally transformed our understanding of the universe. But this technology for all of these instruments, whether they're mine there on the ground or these two in space, are really the culmination of a 400-year history of harnessing technology. And it all started with this kind of natural obsession we have with what you and I call visible light, the light that our eyes can see. And so when we began to understand that we can use technology to make our eyes better, then we naturally focused on that visible spectrum. And so starting in 1609, when Galileo had the wherewithal to turn a telescope to the sky, we have been looking at the universe in the same way that our eyes can. Telescopes in many ways are just bionic versions of our eyes. But as often the case in astronomy, happenstance, serendipity, causes us to realize that there's more things to do than we thought. And astronomy kind of stayed in this mode for at least 200 years until the 1800s. And in the 1800s, William Herschel, together with Caroline Herschel, were engaged in a massive project to map the sky. You can see his famous 40-foot telescope there in the giant gantry in the background. He's the first person to work at cataloging all the deep sky objects, these NGC numbers that you hear us use all the time. He and Caroline were the first people to try and map the Milky Way using that enormous telescope. But he was also interested in this medium that we're using to study the universe, and so he was trying to understand the properties of light. And this artist rendition shows this eureka moment, this kind of happenstance by chance discovery he made. He was putting thermometers in the different colors of the rainbow of light, trying to understand if blue light or yellow light or red light was different. And quite by accident, he had left a thermometer laying right outside the end of the red spectrum, and he noticed that even though he didn't think the thermometer was in light, the thermometer began to climb. It was receiving energy, presumably from light, that his eye could not see. So that was a revelation, and that revelation led to the modern picture of physics that we have about what we call the electromagnetic spectrum. The electromagnetic spectrum is a wide diversity of different kinds of light that as scientists we characterize by a variety of different numbers, but let's focus on what I call wavelength. Wavelength is represented up there by the squiggle at the top. Light is a wave, and the measure of the wavelength of light tells you what the color of the light is. And so right in the middle of this electromagnetic spectrum are the wavelengths that your eyeball can see. And those wavelengths, as indicated by the pictures there, are the size of small unicellular animals, things like protozoans and bacteria and stuff. As you go to the right on this graph, the wavelength of light gets longer, and the infrared light is the light that Herschel discovered. That is about the size of a needlepoint, but your eye can't see it. And as it gets even longer, you get into the microwaves and ultimately the radio. If you go the other direction, the wavelengths get very much shorter. So ultraviolet light's kind of the size of molecules, X-ray light's the size of atoms, and gamma ray light is the size of atomic nuclei. So in the context of astronomy, that was a great discovery. Herschel discovered it, but there was absolutely nothing we as astronomers could do about it because our eye couldn't see any of that light. The only technology we had to use in astronomy was a telescope, which was a bionic form of our eyeball. But if you fast forward 100 years from the time Herschel made his discovery into the 20th century, astronomers began to harness technology that could see, these different kinds of light. And over the course of the 20th century, a ever-growing set of technological telescopes was born, which have slowly expanded to allow astronomers to see the entire universe in all the myriad colors of light. And the Webb Space Telescope is the ultimate culmination of some of that. It is an infrared telescope, and it works there in that part of the spectrum that Herschel discovered. The beauty of this is that as astronomers, we harness the technology because every single kind of light is useful for doing astronomy. And so these are all pictures of a very famous pair of galaxies called the mice. And you can see optical there right in the middle. That's the way it would look to you and I if we looked through a big telescope and could gather all that light in our eyeball. But if we look in the different colors of light, in the different kinds of technologically gathered light that our different telescopes represent, you can see that every different view of these objects gives us a different sense of the astrophysical phenomena that are making them happen. It exposes the lives of the stars, it exposes the gas and dust, it exposes the energetic events going on in the galaxy, and together, astronomers take all this information and piece it together to tell us what's really going on in these two galaxies that appear to be interacting with each other. Now, that was something astronomers had long touted, and when we first began going down that road, we didn't necessarily know that this was going to be the outcome. We didn't know that astronomy was going to be doable in every part of the electromagnetic spectrum, but we hoped it would. And of course, today we know better, right? That's why we have telescopes that work across the entire electromagnetic spectrum. But we learned our lesson well, and so in the mid-20th century, we also said, well, if all the different kinds of light work, maybe there's other things that will work too. And so this built on an early discovery in the early 1900s, the discovery of cosmic rays. Which was originally discovered in a balloon experiment by Victor Hess, which won the Nobel Prize in the 1930s. That has grown into the very modern and very widespread enterprise of cosmic ray astrophysics that involves both telescopes on the ground as well as probes in space. And then by the late 1960s, neutrino astronomy was being born. And those of you who are aficionados of this business know that neutrino astronomy has also grown dramatically, and there are neutrino astronomy experiments all over the world, notably at the South Pole in the form of IceCube, which lies in the southern polar ice. So particles themselves also give us a different view of the universe. In addition to all of these tools we have in the electromagnetic spectrum, we also have astroparticles at our disposal. And so we're very good at learning our lessons from the past. Astronomers are now trying to harness something new to try and understand the universe. And that new thing that we are embarking on here in the 21st century is called gravitational wave astronomy. So let me tell you about gravitational wave astronomy, and the reason I told you about the spectrum here is I'm going to use the electromagnetic spectrum as the foundation for understanding the fact that there's a gravitational wave spectrum. So this is the gravitational wave spectrum drawn out in numbers. I've cleverly color-coded it in purple to red light because we can describe gravitational waves in terms of wavelength the same way we do light. So long wavelength gravitational waves are on the red side of this picture, and short wavelength gravitational waves are on the right side of this picture. But despite the fact that we can do that, we're scientists. We always have lots of different ways of describing the phenomena that we're talking about. Gravitational wave astronomers tend to use a number called frequency rather than wavelength. And so right there, frequency is related to wavelength. So right there underneath is a set of numbers that are the frequency of the gravitational waves that we want to discover. And the little colored boxes then are places where we have figured out how to use technology to observe gravitational waves in that part of the gravitational wave spectrum. Now, over the top of it there, you'll see a number that says period. And that's the connection to astrophysics. Gravitational waves, as we'll discuss in a moment, are generated by masses moving around the universe in dynamic ways. And roughly speaking, that period there is the time scale on which the masses move for us to detect the gravitational waves represented below that name. Okay? So in each of those bands, we have a variety of techniques that we're harnessing. There are even more than this. There are new ideas being thought about and proposed every day. But these are the kind of four main ones that are really far along. Over there on the extreme left, at the very low frequencies or long wavelengths, are experiments that are looking for evidence of gravitational waves imprinting in the cosmic microwave background. Right here in the middle center on the left is a technique called pulsar timing. And those of you who have been paying attention to the gravitational wave news know that our colleagues in pulsar timing in the NanoGrav collaboration here in the United States recently made a big announcement of detection of gravitational waves at these extremely low frequencies. Over there on the far right are a fleet of ground-based interferometers. They are all collaborating together. They are in the United States, represented by LIGO. They partner with Virgo in the European nations and with Kagra in Japan, and there will very soon be one in India as well. And so those operate at short wavelengths, or high frequencies, as we say. And then right there in the blue box in the middle, in the low frequency or millihertz band, as we say, are space-based detectors. And LISA will be the very first of these when it finally flies. So why have I shown you the entire spectrum, and why have we developed techniques and technologies that work across the entire spectrum? Well, the reason for that is because if we take all the things that we know about the universe, and if we think about what kinds of gravitational waves they may generate, and if we think about whether or not they may be detectable by harnessing some technology, what we find is that across this entire spectrum, there are opportunities to observe the universe using gravitational waves. There's no place in the gravitational wave spectrum where we look at what's going on and say, yeah, maybe there's nothing interesting there to see, right? We can already tell you what we can learn as astronomers if we were to build a gravitational wave observatory capable of observing in any part of this spectrum. Now, that's just the stuff that we already know about, the things that we as astronomers have thought about for decades or the century and are able to describe and observe in other ways, or have, seen evidence for but never observed directly. That's all of this sort of stuff. And of course, the great promise of gravitational wave astronomy is that we've never really looked at the universe in gravitational waves until the last decade. The first discovery was made by LIGO and Virgo in 2015, just 8 years ago. And so what we're waiting for, what we know is going to happen, which is what happens in astronomy all the time, is we're going to observe something that we never even imagined. And that's going to really, it'll be tremendously exciting for us as astronomers, but that's always the moment that has the potential to completely transform the way we think about the universe. Okay? So we're going to focus tonight just on LISA. We could have a talk like this every day for a month, and we could then tell you all the possible things that we've thought about and are excited about in gravitational wave astronomy. But I'm just going to focus on this part of the spectrum, the part that LISA is going to observe. And so I'll tell you a little bit about LISA, and then I'll tell you a little bit about these different kinds of sources that we expect to observe. Okay? So what is LISA? LISA, we call it an observatory. It's an antenna, the Laser Interferometer Space Antenna. It is a constellation of 3 spacecraft, so you can see them here in this picture. They are all identical. The final design is unknown still because we are going through that process right now. But the expectation, the design we've kind of centered around for the last 20 years or so is, as you see here, it's something that's a couple meters across. It has a giant solar panel on top that provides the power for the experiment. The spacecraft itself underneath it is maybe half a meter or a meter deep. And then there's 3 of them that are arranged in a triangle that forms a constellation. The 3 spacecraft are independently flying from one another, and they maintain this triangular configuration as they orbit around the sun behind the Earth. The 3 spacecraft exchange lasers. Okay, we'll talk about what we do with that here in a moment. The distance from one spacecraft to the other is 2.5 million kilometers. So we launch that laser. It takes 8.5 seconds to go from one spacecraft to the other. Okay? So as I said, the whole constellation will follow around behind the Earth. It will do this little cartwheel. The spacecraft are not rigidly connected, so each individual spacecraft is on its own orbit, as you can see there. It's just the orbits have been cleverly chosen such that the constellation maintains that triangular configuration that it has. And so that will be stable for something like 10 years. The lasers will run continuously. LISA will operate continuously. And as it moves around the sun there, following the Earth, it kind of constantly changes the face it presents to the sky. And it's that kind of constantly changing face to the sky and this motion around the sun that allows us to basically point LISA, to use it like a telescope. Okay? So that's the constellation. So I've been telling you all about this, and I haven't really told you about gravitational waves at all. So what are these gravitational waves? Now, if you're an aficionado of this and you've heard talks about gravitational waves before, we all say what they are. They are ripples in the fabric of space and time. But what does that really mean? Okay, you will often see movies of it, which are not unlike the ripples you see on a pond if you throw a rock into a pond. But those are good for kind of heuristically helping you understand or think about what gravitational waves may be. But the movie I like to show is the following. So this is a simulation done by our colleagues at Goddard of the slow in spiral of two black holes coming together and merging. And what you see there colored in the space around them is the wave fronts of the gravitational waves. You should notice that they have a very complex structure, and the brightness of the wave that you can see in the movie is a measure of the strength of the gravitational waves. Okay, and so this movie will repeat here. So why do I like this movie? When I'm trying to explain that this is astronomy to people, this movie, much better than the ripples on a pond, shows why this is useful for astronomy. If you look around those two black holes, there are gravitational waves going in every direction in the sky away from the black holes. And so what that means is no matter where you are in the universe, if you have a gravitational wave observatory like LISA, you can receive the signal from these two black holes and be able to interpret and decipher what they're all about from the gravitational wave signal. This is exactly the way astronomy works. Stars, traditional astronomy with telescopes, stars shed light in every direction, and no matter where you and I are in the galaxy, we can take Hubble or take Webb and point it at that star, and we can tell you things about how the star is living its life. And so the same story is true here when we think about gravitational waves. So what are the waves? They're ripples in the fabric of space and time, but they're really a consequence of what Einstein taught us about the universe. These black holes are moving around in space, and so that means wherever you are, if you are trying to sense the gravity from those black holes, if they move, the gravity where you're standing, what we as relativists, gravitational wave astronomers think of as the shape of space and time, it has to change. And that information must propagate at slower than the speed of light, or sorry, at the speed of light or slower, because nothing can travel faster than the speed of light. And so it's that traveling information about how the gravitational influence of the black holes is changing that's propagating across the universe until it washes across our observatory here on Earth. So that's what the gravitational waves are and what they're doing. So Einstein predicted this very shortly after he published General Relativity, but it took a long, long time for us to figure out how do you actually go about measuring these things. Telescopes were easy to build. They're just bionic versions of your eye. But none of us has a gravitational wave detector in our elbow. So we didn't know how to even think about detecting gravitational waves. But we eventually figured it out. It was all kind of resolved and figured out, or at least the basic idea was figured out in 1957 at a conference in Chapel Hill. And so this movie will kind of capture the basic idea. So what you're seeing here is an array of dots. And what I want you to do, we'll start with the array over here on the left. I want you to just focus your attention on the dot in the very center of the grid. Okay, now each of these dots represents some little object, a little massive object, okay? And gravity influences is mass. And so if the gravitational influence in this part of space where this array of dots is, this array of masses is, then that gravity will change how the array is situated. Okay, so focus your attention on one in the middle and then pick some other one somewhere else in the grid. And now imagine a gravitational wave propagating straight into the screen or straight out of the screen. What's going to happen to the grid of particles? Well, what gravitational waves do is they change the structure of space and time. They stretch the fabric of space between the dots. And so this is what the effect that we're looking for is. Relative to one dot, the one in the center, if I look at any other dot in the grid, a gravitational wave passing through this part of space will change the proper distance, as we say, between that dot and any other dot. You'll notice it changes it in an oscillatory way. It goes back and forth. It stretches, then compresses, then stretches, then compresses. So that's the wave-like nature going by. And then you'll notice that the effect is more prominent the farther away from your center reference dot you actually are. And so this is why gravitational wave observatories are big, is because we're trying to detect these small changes, and they're easier to detect over large distances. So the reason there's two arrays here is gravitational waves come in two flavors. This flavor that you're observing right here is called plus, so you can imagine drawing a gigantic mathematical plus sign over the grid here, and that is the direction that the masses are moving as the gravitational wave goes by. The other one we call cross. You imagine drawing a big X through this, so that's a mathematical cross for those of you who remember your calculus class or your physics class. And so this flavor of gravitational waves is slightly different. It's independent of the one that's shown on the left, but the two of these together, we as astronomers, if we can measure them, we can use this information to disentangle a variety of properties about the source that's generating gravitational waves for us. Okay, so this was the thing that physicists figured out in the late 1950s, is this is the effect that we have to look for. So the question is, okay, great, how do I measure all these little changes in distance and all these distortions that I'm showing you? Well, the basic idea is you take your grid and you pick any of the dots that you want, and you just develop a really exquisite technique for measuring the distance between them. And so this is what gravitational wave observatories built out of lasers are all about. The corners of the observatory, the mirrors in the experiment, are reflecting laser light back and forth between them. And that's true for the ground-based experiments like LIGO there, but it's also true for an experiment like LISA, which is a giant triangle in space. And so we shine lasers back and forth between those dots. And as the dots get distorted because of the passage of the gravitational waves, the time it takes the laser to fly from one to the other changes. And that measurement constitutes a direct measurement of the gravitational wave as it's passing through this region of space. So that's the game. And it's not like normal astronomy where we can take a picture, right? It's literally a measurement of the stretching of space and time. But we can nonetheless take that information and turn it into an astrophysical representation, an astrophysical story about the source that created the waves. Okay, now I'll tell you about that here in a minute. Now, you can't do this, right? NASA and ESA and the National Science Foundation, they're not going to let you do this unless you show that you can actually make the kind of measurement I'm describing to you. And so we've certainly done that with LISA. In 2015, we launched an experiment called LISA Pathfinder. So this is a single spacecraft, roughly the size of a LISA spacecraft. There's not two, so we can't do the full gravitational wave measurement that LISA will do. But deep down inside of Pathfinder is basically a little miniature version of one of LISA's arms. There's mirrors that are bouncing lasers back and forth, and we're showing that we can accurately time the laser motion between those mirrors. What you see up there in the upper right is one of our mirrors that we have on LISA. So this is usually called a test mass. It is a cube of gold and platinum. It's about 4 centimeters on the side, and it weighs about 2 kilograms. Okay, so this is the technology, right? This cube of gold and platinum flies inside of that spacecraft all by itself. It's isolated, it's floating. The spacecraft is all around it, all the lasers shining on it, and the container that it's contained in are all around it. But the goal of the mission is for the spacecraft to be isolated from the cube. Because the cube is being responsive to the gravitational waves. And if the gravitational waves do something, if gravity pushes the cube, we don't want to be touching it. We want it to respond to gravity alone. And so we bounce the laser off that shiny surface, and that's how we monitor the position of the cube. Now there in the lower right, you'll see a replica of the cube in my hand there. So that is a replica made out of tungsten. Okay, so the reason the replica is made out of tungsten is because they don't let people like me and you touch the ones made out of gold and platinum, right? We get fingerprints on it, we lick it, we drop it, you know, that's all bad. But tungsten has almost identical density to gold and platinum. So that cube I'm holding in my hand there is the same size and same weight as the real cube that flew on Pathfinder, as the real cube. And those of you who have seen me give talks before or have been to any of my other public talks know that I carry this cube around with me to talks. And so you can walk around and you can touch it and take a selfie with it. It's very heavy. Those of you who have played with tungsten before know this. Tungsten is very, very dense. And so, you know, you just have to be careful when you take your picture with it. So, okay. So this is the LISA cube. And this is the heart of our technology, the ability to isolate something so that there are virtually no forces acting on it and then very precisely sense its position is the technology that enables LISA to work. Okay? So, that's all great. We can build a gravitational observatory. What are we going to do with it? That's the goal. So, the gravitational universe that you may have heard about, such as the universe discovered by LIGO, Virgo, and Kagra, is all about what I'm going to call small systems. Now, these aren't small by human standards. They are small by the standards that I'm about to tell you about in the context of astrophysics. They are very fast. They're moving around each other in fractions of a second. So these are stellar mass black holes. These are neutron stars colliding. If we get lucky someday, there will be things like supernovae. By contrast, LISA is going to be big systems. By big, in this context, we mean the orbits are much wider. They're much larger than the orbits that LIGO, Virgo, and Kagra will observe. These big systems are going to have orbits that take 10 seconds to 1 day. So they're still tiny compared to what you and I are used to here in the solar system. Mercury, the closest planet to the sun, has an orbit of 88 days. But we're talking about massive objects, neutron stars, black holes, white dwarfs, going around each other in 10 seconds or 1 day, not the 88 days that Mercury goes around. Okay? So these kinds of things that we observe in gravitational waves, we describe them in the kinds of physics that you may be used to if you think about orbits in the solar system, but they are extreme in the context of what we encounter in everyday life in our region of the galaxy. So this is the game here, and so let me tell you about a few of the different kinds of source classes that LISA is going to observe. So Frank led the evening talking about galaxies, and so galaxies are certainly one of the things that we're very interested in. Galaxies come into the LISA science in many different ways, but what I'm showing you here is a collection of images from Hubble of interacting or colliding galaxies. So there are some 500 billion galaxies in the universe, and if you look long enough, you will find galaxies live together. We live in a small group called the local group. The Virgo cluster, which is nearby, has some 2,000 galaxies in it. As you go farther out into the universe, you find lots and lots of clusters of galaxies. And when galaxies live in such close proximity to each other, sometimes they see each other and their gravitational attraction will draw them together and they will ultimately collide. Okay, so this is a collection of such images of interacting galaxies. Sometimes they collide and go through each other, but sometimes the collision is just slow enough that they stick together and they merge and they form a new, bigger galaxy. So why is that important in gravitational waves? Well, the centers of most galaxies, as we understand it, has a very large, massive black hole at the center. And so when the galaxies merge, those large black holes, just like rocks in a pond, sink to the center of the galaxy. And so in the centers of all of these galaxies that have collided, there are, we expect, going to be black holes that are slowly orbiting around each other and getting closer and closer and closer together. And when they get to within about a year of merging and becoming a larger single black hole, then they are going to emit gravitational waves that are observable by LISA. Okay, so what I have here, so this is just an image of that very last part of the in spiral of these supermassive black holes. And one of the things that we do to make this gravitational wave stuff a little more accessible is we can take our data and we can turn it into sound. Okay, so waves are waves are waves, and our data just looks like a bunch of squiggles. And one of the things most of you know is that if I were to take your phone and, download all the music you have on it, it looks like just a bunch of squiggles. But your phone knows how to take those squiggles, and when I push it out through the headphone jack, it turns it into audio. So if I steal your phone and I replace all the squiggles on your phone that are the latest Taylor Swift songs with squiggles that represent LISA data, when you try and play your music, you're going to hear the gravitational wave data converted into sound. Since none of us have a sense that's built for detecting gravitational waves, that's great, because we do have an auditory sense. And so I'm just transforming the data into something that we can experience. So I have two sounds here that I'm going to play for you. These are both the same kind of system. It's a 10 solar mass black hole falling into a 10,000 solar mass black hole. Okay, so this is a kind of source that we've not seen. It's a kind of source we expect should exist. And so if it does exist, it will absolutely be detectable by LISA. Now, the difference between these two sounds is both of them are 10 plus 10,000, but the difference is the very first one is a completely circular orbit, just slowly shrinking a little bit over time until the black holes merge. And then the second orbit is exactly the same system, except that the orbit is oval shaped. It's eccentric, it's elliptical. And so what you will hear is that the two sounds, even though they're both the same black holes, their orbits are different, and so the gravitational waves are different. And what you should take away from this is why we can actually do astronomy, because the gravitational waves themselves actually represent the physics of the system. Okay, so I'm going to play the first sound here. And the audio on the broadcast here is a little weird, so I'll have to talk over it a little bit just to kind of make sure you can hear it. But here it goes. So the sound you hear, the pitch, is related to how fast the orbit is going around. And as the orbit shrinks, it goes faster and faster and faster, so the pitch goes up. And when it goes up, it gets very high-pitched, it gets very loud. That's because the gravitational waves are getting really intense. And then the moment the two black holes merge and become one, then it vanishes. The gravitational waves end because the masses aren't moving around anymore. So we call that kind of ramp up in sound and pitch, that whoop, we call that a chirp. Okay, and so when we say gravitational wave chirp, that's the kind of signal that we're talking about. So here's the other sound. So again, this is a 10 solar mass black hole falling into a 10,000 solar mass black hole. And you'll see that the signal, the gravitational wave signal, is different, which you can hear by the fact that the sound's different. Okay? So it probably sounds a little bit like the car you had in college, right? Okay, it's got a big knock in it. And what that knock is in the eccentric orbit, the moment when the black holes are close together, you get that pop, that clap. And then when they're far apart, there's a little bit of quiet. And over time, it gets more and more circular. That chirping sound, just like we had out of the last one. Okay? So real astrophysical information is contained in these orbits. And one of the things that we've been doing, people like me, I'm a theoretical astrophysicist, I spend my time simulating this sort of stuff, is we figure out what those signals sound like, what they look like, so that we can actually search for them in our data. Okay, so these massive black hole binaries are one of the things that people are most excited to see. They are part of the great mystery about how black holes formed and how they grow. How did the quasars turn on? How early did they turn on? All of that information will be things that Lisa can think about and address by detecting big black holes. Now, little small things fall into black holes as well. So we also think about something called extreme mass ratio inspirals, or EMRIs for short. So these are small objects like neutron stars or stellar mass black holes that have been captured by a single black hole down at the center of our galaxy. Some of you may remember that a Nobel Prize a couple years ago was given for studies of the black hole at the center of our galaxy. So the UCLA group is one of the groups in the world very well known for studying small objects around the black hole at the center of our galaxy. And there will be black holes in the universe, which has things like small black holes going around them. And these gravitational waves will be detectable by Lisa. Now, the thing that's exciting about this is you'll see that orbit is kind of going all over the place around the black hole. This is something we call zoom whirl orbits. It zooms around far away, and then it comes in and it whirls around the black hole and goes away in some other direction. The fact that it's kind of mapping out all the space around the black hole is related to something we call geodesy in the space biz. We do this around the Earth. You watch a satellite go around the Earth, and the Earth's gravity affects where the satellite goes. And so we can use that to map out the gravitational field of the Earth. And so these EMRIs, we're going to do the same thing. We're going to map out the space-time around the massive black hole, and that will allow us to tell what the properties of the black hole are and decide, are these the black holes that general relativity predicts are the ones that we should see? Okay, so this is very exciting. We'll use this a lot, and hopefully it'll tell us a lot about the nature of these black holes. It will also tell us a lot about how often stuff gets sucked up by black holes in the centers of galaxies, which is something those of us who study the nuclear areas of galaxies are very interested in. Okay, so that's one of our second big source classes. Now, the other thing that we're interested in, this is what my group mostly works on at the moment, is what we call ultra-compact binaries in the Milky Way. So if you've gone out and seen the Milky Way, you know that it's this vast band of light overhead, but that's also our home galaxy. That band of light, when you see overhead at night, is the light of some 400 billion individual stars. And most of those stars, or some high fraction of those stars, are in binaries. That is, they go around each other, not unlike a planet goes around the sun. But very often, when the stars die, their stellar skeletons can get very close together, like that little pair down there at the bottom, and they will orbit around each other on very short time scales, typically around 1,000 seconds or so. And if they're making an orbit around each other at that very high rate of speed, then they are emitting gravitational waves that Lisa will be able to observe. Okay, so there are going to be some very large number of these in the Milky Way. We estimate, this is kind of the research that a lot of us are working on, how many there should be. There should be some 10 million individual ultra-compact binaries in the Milky Way. So these are binary stars, these 1,000-second orbital period, but they're comprised of white dwarfs, a dead star about the size of the Earth, what our sun will become when it dies, a neutron star, or a black hole. Okay, and so they're going around each other, and so they represent the stellar graveyard of the Milky Way. Okay, so there are some 10 million of them, and that means that all of them are radiating gravitational waves at the same time, and so we have to figure out what to do about that. So the way we describe this is we say, imagine you go to your cafeteria at lunch. Okay, and at your cafeteria at lunch, everyone is talking at the same time. and everyone's talking in language, and so you can recognize that, but you can't really make out all the individual conversations. So that's the sum of all the signals from all over the cafeteria. And in a very similar way, Lisa is going to be able to sense that background hum of all the ultra-compact binaries in the Milky Way. But just like in the cafeteria, you can still make out some conversations. You can make out the conversations of the people close to you. So we're going to be able to sense the gravitational waves from the ultra-compact binaries from the white dwarfs closest to us. And you can also hear the conversations from very loud people. And so there will be a few very loud systems strewn across the Milky Way that we are going to be sensitive to. And so, yes, we're going to hear that hum of gravitational waves from the entire galaxy, but there will be between 10 and 30,000 individual white dwarf binaries that we will be able to pick out. So we've done a lot of thinking about this resolvable population, as we call it. And this is a movie that my colleague Tyson Littenberg made, flying out from the sun. And as we fly out from the sun, you will see dots appearing. Okay, the big black dots, those are white dwarf binaries that we already know exist. We can see them in telescopes. Okay, you'll see the entire galaxy is there. So every dot represents one of these resolvable white dwarfs that Lisa can see. You see that we can see white dwarf binaries across the entire galaxy. And then you'll notice there's two colors. There's red and there's purple. And the red ones are the ones that only Lisa can see. They're too far away and too faint to be seen by telescopes. But every purple one is going to radiate gravitational waves that Lisa can see, but also be bright enough that we can point a telescope at it and see it simultaneously in light and in gravitational waves. So some of you may have heard the term multi-messenger astronomy, and this is the gold mine of multi-messenger astronomy. There are going to be more multi-messenger astronomy opportunities with LISA than for any other gravitational observatory in existence. There will be many thousands of individual white dwarf binaries. The supermassive black hole binaries that we talked about a few minutes ago, those also may very well have electromagnetic counterparts, things you can see with telescopes. And the merger of using gravitational waves and telescopic data at the same time promises to be very rewarding for expanding our understanding of all of these different sources. So we're very excited about that, and we're putting a lot of time and effort in right now to try and understand how do we use telescopes and LISA together. We got 10 years to figure this out, so we're going to figure it out now, so we're ready to go. The fact that LISA can see the whole galaxy is also very beneficial. So you can see here, these are two simulations from my group. We simulate all the stellar graveyard of the Milky Way, and then we ask, how does LISA observe that graveyard? And because we don't exactly know all of the properties of the Milky Way, we're looking at how the Milky Way looks different based on our uncertainty or things that we don't understand the Milky Way. And so what you can see here in this movie is that if we make different assumptions about the Milky Way, all well within our understanding of how the Milky Way may be, it looks like there are going to be opportunities for LISA to really transform the way we understand the shape and structure of the Milky Way. And so this is a very active research that we're working on right now, and it's something we hope to be able to say more about here very soon. Okay? So that's just a little thumbnail scratch on the surface of what LISA is going to be able to do. The scope of LISA science goes very deep in any of these areas to tell us about the properties of black holes, to tell us about the properties of galaxies, to be extended to understand science that leads to those things, like how are stars born, what's the stellar evolution history of the galaxy, how often do galaxies merge, where do black holes grow, do they grow by accretion of gas, do they grow by merger with black holes? There's all kinds of different ways that the LISA data will inform the kinds of astronomical questions that people are interested in. And so we're very excited that things are moving forward and looking up right now. The gravitational universe, which we are all going to see in about 10 years, is going to be a very dynamic and exciting place. It's really going to be very different from the universe that we understand now. And so it's very exciting. So the last thing I want to tell you then is to remind you all something which I'm sure you know, which is astronomy doesn't happen because single people like me are out there doing it. It is really a collaborative effort to build instruments as large and complex as LISA, to build instruments as large and complex as LIGO, to build instruments as large and complex as Hubble and the Webb. We can't do it without all the people who are involved. I certainly can't do the work I do without my students. So this is my current group of students who are all working on LISA-related stuff with me. So if you happen to see them walking on the street or working on their code in the coffee shop, say hi to them, tell them you're excited LISA's going to happen, and they'll talk your ear off for an hour. My three most recent PhD students are up there at the top. They're all doing awesome things as well, and so we're all kind of very thrilled that this is moving forward. But like I said, it's not just us. There is huge teams of people. There are engineers, there are optical physicists, there are computer programmers, there are administrative assistants, there are welders, there are titanium miners, there are truck drivers who make all of this happen. And science, in the end, is about these awesome discoveries that we're making, but in the end, it's really about all the people who are dedicating their lives, dedicating their smarts, dedicating their efforts to making this possible. And so I certainly want to thank all my colleagues who work on this and congratulate all of them on getting to this point where we are today. So I always leave you with a few things to read. So here's a few books about gravitational waves that if you're interested in continuing your studies, these are all great places to start. The lower left book there by Marcia Batusiak, it's an award-winning book. It's mostly about LIGO, but it'll kind of tell you about the journey to deciding how it is that we thought we could discover gravitational waves and ultimately how we did it. Both the book by Brian Clegg and Govert Schilling there are kind of very broad books about gravitational waves. And then Kip's book up there in the upper right is a very general book about all kinds of different things in gravitational physics, which includes gravitational waves. Okay, and then down there at the bottom, there's a link to my blog again, as well as to the various LISA sites where you can get more information about LISA and the awesome things that we're going to do. And with that, I will say thank you for your attention, and I will pass it back to Frank.
All right. Thank you, Shane. That was wonderful to see where gravitational wave astronomy has come because, you know, when I was a graduate student way back when, there was lots of discussion of, you know, when we're going to be able to you know, observe gravitational waves and all of the anticipation of it. But, you know, there's a tremendous amount of technology and, you know, computer development. I mean, you know, so many things in astronomy have, you know, just been advanced just because, you know, the technology has gotten so much better. So what were the most significant technological changes that enabled gravitational wave astrophysics in the 21st century?
Yeah, that's a great question. So you know, gravitational wave astronomy, when it started, was not built with laser measurements like LIGO and LISA are using right now. It was originally built using something called bar detectors. And if you go to the LIGO sites, they have the original bar detectors on site and you can see them. But the idea was you take a giant bar of aluminum. Okay, so Joe Weber, who was at the University of Maryland there, was one of the first pioneers of this. The idea is when a gravitational wave goes by, just like I showed in that grid, it kind of stretches the space-time between any two little masses. So imagine one end of the bar is a little piece of mass and the other end of the bar is a little piece of mass. The gravitational wave is going to stretch it, but the intermolecular forces of the bar want to keep it together. And so after the gravitational wave goes by, it lets go, and the bar kind of rings like you tapped it with a hammer. And so the very first experiments were basically microphones taped on the sides of those bars looking for anomalous vibrations of that sort. Now, we know a lot about, you know, materials physics now, and we can do the analysis and can convince ourselves that there's no way that experiment would have ever worked given what we know about astrophysics today. But those were the experiments that really laid the groundwork. And so the laser interferometer technology, the ability to isolate things so that they're so quiet, nothing's shaking them. So for LISA, that's isolating it down in the middle of the spacecraft, and it's not coupled to interplanetary magnetic fields, and it's not feeling from too many twist ties on that side of the spacecraft, and right, all of these sorts of things. That ability to isolate was really the breakthrough that makes LISA possible, and that's what we demonstrated on LISA Pathfinder. If you go read the stuff the LISA Pathfinder team put out when they were doing all of their public press, right, the way they described their experiment is it's the quietest place in the solar system, right, and what they mean by that is nothing is influencing that cube except what we're looking for, which is gravity. And so that was really the breakthrough there. There's all kinds of other things, related to the lasers and how do you control spacecraft and all of that really enables LISA. But it's it's like all big complex experiments, right? It's just one thing at a time. And you just get up in the morning and you solve one problem, and then you solve the next one when you're done. And eventually all of the solutions accumulate until you have an experiment that's going to do awesome astrophysics.
Yeah, except that you're trying to do this in space, so
that makes it triply hard, right?
You're not really able to test it in your laboratory.
That's right. Yeah. Well, even there, how do you test this stuff on the ground? That's a big experiment. And so one of the things, my experimental colleagues are like the cleverest people I've ever met. One of the things we do, some of you may know about something called a torsion pendulum. So this is a pendulum where you kind of suspend a beam on a wire, and then you put masses on the end of the beam. So it's like a teeter-totter hanging on a wire at the center. But what that does is it cancels out the Earth's gravity, and you can do gravitational experiments horizontally. And so in that kind of environment, you can do something that kind of approximates what we might encounter in space. And so there's lots of these torsion experiments from our colleagues in Italy. We have a really good group at University of Washington, another really good group at the University of Florida who do those kinds of experiments. So,
all right.
Yeah.
Yeah. The challenges, obviously you've met them so far.
Yeah.
We're going to bring Grant in. Grant has been monitoring the YouTube chat. And people have been asking, I've watched it stream by a lot. There's a lot of questions there, Grant, tonight. A lot of comments here tonight. I kind of expected that because of the gravitational wave.
Generates a lot of interest, so we'll do our best. So what do you got, Grant?
Audience, I will do my best to get through as many as I can. Okay, so let me just pick up kind of where we're already on the subject. How will the LISA engineers or operators manage to keep the onboard lasers aimed in the right direction? Is it an active or passive process? Yeah, hard to imagine it's set and forget.
Yeah, that's a great question. So our everyday experience, the experience you and I have with lasers, is often with laser pointers, right? And so, I take a laser pointer, I shine it across the room, and it seems like the laser stays very, very small. But in reality, laser beams spread out as they travel through space. And so when we launch the laser beam from LISA, it will slowly spread out as it travels to the distant spacecraft. And so when it gets to the far end, the laser spot is going to be about 10 kilometers across. Okay, so we don't have to actually get the little laser pointer dot in the right place, but we do have to get that 10-kilometer spot in the right place. And so the way it's going to work, we have a cool movie about this that actually I probably have it in my extra slides, but you can find it online if you go to the LISA website, I think. The spacecraft will orient itself, and it has a set of telescopes that we call star trackers. So instruments like Hubble and Webb also have these. It's how they know where they're pointing. They look at all the stars in the sky, and they say, okay, there's this star, and this star, and so that's how I know where I am. And so LISA will do that, and it says, based on where I see the stars, I know where my partner spacecraft should be, and it will shoot its laser in that direction. And so once the spacecraft acquires, then it shoots straight back, and then they'll acquire the third one in the same way.
So I'm sure it's on JWST as well, but that's the same system they use to make up for, but to both make more accurate and to make up for when we have gyro issues on like HST, right?
Yeah.
It's the geopositioning based on the stars and other platforms.
Yeah.
So, I mean, I'm assuming that the three LISA spacecraft are constantly measuring distances between each other due to the time delay, et cetera.
Yes.
And that's an incredibly important component of keeping it accurate and all this. So you said there was like an 8.5 second time difference on nominal?
Yeah.
On that?
So you have to lead, right? You have to, right? This is those of you who do like trap shooting or something, right? The object's moving, and so you have to lead with it. So that's part of the algorithm for the laser acquisition and following. So yeah.
Cool. And what about the station keeping? Because like for JWST, every 2 weeks we have to do a little station keeping thruster fire. Do we have to do an awful lot of that? Is there a limitation to the length of the mission due to propellant because of that?
Yeah, so that's a great question. So you were asking about technology, right? So another technology that Lisa needs. So this kind of flying that we do where we have the cube isolated by itself is usually called free fall flying. And so the idea is the cube's going to go where it wants, and the spacecraft has ways of paying attention to the cube. And so if the cube moves this direction, the spacecraft has to follow it. And that direction may be in some direction that the spacecraft isn't already going, or that it's being pushed. For instance, the light from the sun is constantly trying to push the spacecraft, out. And so the spacecraft has to have a way to do that. And so there's a set of thrusters around the spacecraft, and they generate micronewtons of thrust. So that's a physics statement, okay? So what's a micronewton? A micronewton is a force equivalent to the weight of a mosquito's antenna sitting in the palm of your hand. And so the way these thrusters work is they just put out little bursts to push the spacecraft to follow that cube, and that micronewton burst is all we need to kind of keep on trajectory.
All right, cool. So basically your cube is running its trajectory, and the spacecrafts have to keep up with that trajectory.
The cube is boss. Yeah.
All right, Grant. What else we got?
All right. I'm asking this one just because I'm also curious. If a person were to stand on an infinitely sensitive scale and a gravitational wave passed through them, would they gain weight, lose weight, or would they be unaffected?
So that's a good question, and it's a complicated question because it depends on the direction the gravitational wave is passing through you. Okay. So let's imagine the scale's measuring forces in the vertical direction. Okay? So what we said the gravitational waves do is if they're traveling in a direction, they make changes in the direction that's perpendicular or transverse to the direction the gravitational wave is going. So if I'm standing on my scale and the gravitational wave comes straight down through my head, the scale can't tell.
Okay.
Okay. But if I'm standing on my scale and the gravitational wave comes in from the side, it's going to stretch and pull me like this. And so what will the scale see? Well, that depends on how the scale gets stretched itself and how I get stretched. But in the end, all of my mass is still pressing down on the scale. So the scale doesn't think there's new mass or less mass. But if the scale spring gets stretched by the gravitational waves, then it may read out something different. And I've never done that calculation, but it should, I think, make a difference. It's like the bar I was telling Frank about at the beginning. In my head, that's what makes sense. It's just like the bar. But it absolutely will depend on the direction the gravitational wave is traveling. So.
And Shane, one thing that you didn't mention that I've heard people mention in other gravitational wave talks is the scale of this stretching and shrinking is incredibly small.
Yeah.
Right. And so
make
sure the public knows that.
Yeah. The LIGO measurement is often described. The very first gravitational wave measurement stretched LIGO's arms by less than the diameter of a proton. Okay. And Lisa, the kind of standard measurement that we make down that 2.5 million kilometers, that length between the spacecraft and our ability to time it is about the size of what we call a picometer, which is 1/trillionth of a meter.
Okay.
So very, very tiny.
People that, they don't think that, suddenly they're going to wobble like this.
No,
gravitational wave is coming
right.
through you.
Yeah.
Sorry, you're not going to feel it.
And that's because the sources are so terribly far away, right? If you were up close to it, right? If there were a binary black hole outside the orbit of Pluto, then, we could probably feel more gravitational waves than we feel, but we don't. Everything's really, really far away. So the extreme universe is not in our backyard.
Which is good.
So that leads directly to the next question, which is after the two black holes that you had mentioned merge, does the resulting black hole vibrate or rebound in any way that might be detectable?
Yeah, that's a great question. So the answer to that is yes, and we don't normally talk about that, or it's in the sounds I played for you. It's just it's below your ability. But what happens when the black holes first merge is, if you go watch movies of this online and pause the movies, you can see this. It's in a highly distorted state. Okay, so it kind of looks like a blob of cookie dough that's been mushed out into a dumbbell shape, and that object is still rotating. And because it's still rotating and in this distorted shape, it's still going to emit gravitational waves. Those gravitational waves are what we call ring down waves, and they will persist for just a little while because gravity wants to pull the black hole into a normal spherical shape. And so it takes that distended blob, and over time, it radiates the gravitational waves until it pulls that black hole into a highly symmetric shape. And once it reaches that highly symmetric shape, then there are no more gravitational waves to detect. But there's a whole enterprise that we astronomers are working on about those ring down waves and how can we measure them and infer the properties of the black hole from them. How fast is the black hole spinning? Is it really like the Kerr black holes from general relativity? How quickly does it settle into this symmetric shape? And is that symmetric shape like a pancake, or is it perfectly spherical? What does it look like? And all of that information is in those ring down waves.
Gotcha.
That's a great question.
I'm going to keep going with the black hole while we're on the topic.
Okay, that's fine.
People will continue to have black hole questions all night long. So
that's right. That's the way it goes.
I'll make this the last one for now.
Okay.
Is it common to have collisions around a black hole, as there isn't like a single orbital plane or direction as things are attracted towards it based on speed and proximity?
Yeah, so that's an interesting question. We spend a lot of time asking ourselves what the environment around massive black holes at the centers of galaxies are like. If you go watch the movies of the stars that we see around the center of our own black hole in the Milky Way, you can see the stars are kind of all over the place and going in different orbits and in different shapes. And so what we do now, because we can't resolve the centers of galaxies other than our own at that level where we can see the stars moving around. So we spend lots of time simulating what the centers of galaxies might be like, trying to answer exactly this question. Okay, and so there are a variety of ways that you could frame that question such that we can try and answer it. But one way we might answer it, might ask it, and this is something that I've worked on in the past, is how often will a black hole like the Milky Way have something fall into it? How often will it suck up one of those stars? And the answer is something like once per million years in a galaxy like the Milky Way. Okay. So that's not very often. But if you think about the whole volume of the universe that Lisa can see, there will be tens of millions of galaxies that we can see. And so we should see some of these every year, because over tens of millions of galaxies, something that happens once every million years will happen once 10 times a year or something like that, right?
And it's that ability to see these observations at such great distances across the universe that makes this technique so powerful.
Absolutely, yeah. And that's why we focus so much on being able to see as far as we can, because these events are rare. So we have to see that big volume in order to see these events. And that'll tell us something about to answer that question. How often does it really happen? So.
Right, and that raised a question in my head, because I'd never really seen a calculation of how we think black holes build up. Right, going from stellar mass to intermediate mass to supermassive to supermassive black holes. You showed you played a sound from a 10 solar mass black hole accreting onto a 10,000. Is that what we think is typical? What is the typical accretion? Growth rate.
So we don't know the answer, right? We have answers we like, but we don't know the answer. And so, in fact, there's kind of two parts of this question. So one question is, how big were the very first black holes? And then after the first black holes formed, how did they grow over time? And so I'll tell you two things about that, and then Lisa will tell us even more when we fly, because we'll have data about these scenarios. But one thing is, there are questions about the very first black holes. And so one of the ways the very first black holes could have formed is from enormous stars that formed when the first stars were born. And so stars in the very beginning of the universe are different than stars today. They can be very large because they're almost pure hydrogen. And so one of the answers one of the questions that Webb is going to try and answer is tell us something about those very first stars. And so we should be able to know something a little bit more about those very first black holes as information from Webb comes back to us. The other thing, our colleagues who are doing pulsar timing, as their data gets better, what they're seeing, for those of you who haven't heard the result that was announced, I think 2 or 3 months ago, they are seeing the background hum of all the black holes in the universe, kind of the same way Lisa's seeing the background hum of all the white dwarfs in the Milky Way. So if all the galaxies have big black holes in them, the pulsar timers are seeing all the binary black holes talking together at the same time. And the exact shape and content of their signal depends on whether or not the black holes grow by crashing into each other or whether or not they grow by accreting gas, for instance. And so they will be able to say something about this by the time Lisa flies as well. And so you can kind of see how astronomy is this big interlocking puzzle, right? We all kind of depend on each other in order for us to dissect this kind of really tremendously complicated story that is the universe, which is kind of cool. This is why interdisciplinary science is what we do at Sierra, right? So, yeah.
I love it.
Grant?
What do we got? What else we got?
When LIGO made its first detection of gravitational waves, the team spent a very long time verifying that it was in fact a real result rather than a false positive.
Yep.
How will LISA observations be validated?
Yeah, so that's a great question. So the era that Lisa will fly, so there's 2 answers to that. So the first answer is the era in which Lisa will be flying is very different than the one where LIGO made the initial discovery, right? By the time Lisa flies, and we're already in this era, gravitational astronomy and gravitational data is a tool that astronomers use every day. Right? We're used to it. We know how to think about it. We've seen enough sources that we're confident the technology works. We're beginning to understand what the implications of our data is and what high quality data looks like and what poor quality data looks like. We're beginning to be able to understand how to extrapolate and connect it to other areas of astronomy. So our confidence level has grown because at the moment LIGO made the first detection, we had never seen a gravitational wave before. Right? We knew what we were looking for, but that's different than having the data in your hand and being confident in what you're thinking about. And so, it reminds me, there's this folklore about Galileo. When he first pointed the telescope at the sky, he wasn't sure if the telescope was lying to him. And so as the folklore goes, he used his telescope to look at an Italian coin across the courtyard of his villa, and then going up and looking at the coin up close with his eye to convince himself the telescope wasn't lying to him, right? So we used to not trust telescopes, right? But now we do. And so we're going to be in that state when Lisa finally flies.
Right. Yeah.
There will be the immediate, yeah, what?
I was just going to say, we've gotten so many of these observations that we're starting to fill out the characteristics of all these compact mergers.
Yeah, the LIGO catalog already is at like 100 something objects, right? So they've just in the 5 years since detection, that's grown from 1 to 100. So it's definitely a lot. Yeah. Then the other thing about Lisa is the very first thing that we'll be confident in are the white dwarf binaries, because we've already seen a whole bunch of these in telescopes. There's some of them that we can measure their orbits shrinking just based on telescopic measurements, and that will directly be comparable to what Lisa measures. And so we're going to know right away that it's working as expected, right? So those known binaries are, if you want, a validator for the expectations. So.
Okay, I think we have time for just one more question. I know that there are tons of them out there, but just one more.
All right, so one more. In theory, could one use a Bose-Einstein condensate as a gravitational wave detector by looking for perturbation in the BEC caused by the gravitational waves passing through it?
Yeah, so that's a great question. So right now there are all kinds of different ideas about how can we detect gravitational waves. Okay, and so there are ideas based on technology we can build and control in the laboratory. There are ideas about how to use nature as our laboratory. So pulsar timing is a second example there. We're looking at distant pulsars and we're measuring their signals they send to Earth to detect gravitational waves. Bose-Einstein condensates are the same way. We can certainly make Bose-Einstein condensates in the laboratory, but there are also kind of astrophysical questions about whether or not these things exist in nature, something we call a boson star. And so if you know the properties of those objects and you know how they behave, they are distributions of mass. If they have a very precise, well-known shape and you can measure it, then a gravitational wave passing through it should perturb it. And so in principle, right, it's not, I don't know that anyone sat down and done this calculation, but it's not an idea that a physicist will just be like, psh, right? Because yeah, we're looking for ways that this kind of stuff might work. And if there's some controlled environment where you can know and monitor the physical properties of a system, then you can almost certainly imagine ways to turn it into a gravitational wave detector. Whether or not you can compete against other things that want to distort it, that's always the battle. It's not detecting the gravitational waves that's hard. It's getting the thing isolated from everything except gravitational waves that's hard.
Signal to noise.
Signal to noise, exactly.
All right. Thank you so much, Shane. This has
Thank
been
you, guys.
wonderful.
This was great.
Wonderful for learning. Next month, March 5th, we'll be talking about the total solar eclipse coming in April. So please join us for that time. All right. Take care and have a great day.
Thank you all.
Thanks, everybody.
And